A very good afternoon to all. Myself Amandeep Kaur. I am here for presenting my lecture on perspectives and the transformations. Let's start with the topic what we are going to cover today is, first of all we will discuss the what is three-dimensional projection, then we will discuss the 3D viewing, projections, perspective projections, parallel projections, then we will flow light on the specification on arbitrary 3D views, and the last is graphic pipeline revisited. So, what is projection? Projection is a key term which is used from converting 3D to 2D, that means 3-dimensional to 2-dimensional, is defined by straight projection rays projector emanating from the center of the trajectory, passing through each point of the object and intersecting the projection plane to form a projection. Means what we are seeing from one side, the angle of elevation is known as projection. Here you see in the example, here is the object AB. When you see it from one side, it gives some one portion is covered under your eye. The thing is known as projection. So what is 3D? Today we all heard about 3D, 3D, 3D. What is 3D? It means three-dimensional. The art of representing a three-dimensional objects or a scene in a 2D space is called projection. So projection needs display devices for what obviously a screen, that is a 2D, and projection is how do we map a 3D objects to the 2D space. This is all about the projection. As we all know, 2D to 2D means two-dimensional view. Projection in the 2D space is a straightforward, that is 2D window to world and a viewport on a 2D surface. In this clip, what we would not be shown in the 2D window and map the remainder to the viewport. But 3D to 2D is more complicated, and the solution is projection. When we transform the 3D objects to the 2D plane, we said we did it projection. Here you see a scene. In this scene, one kettle is placed over this chair, and you see chair is placed and you see the parts of this kettle or parts of this chair. But when you see through this 3D camera, here you see all of the sides of the chair, all of the sides of the kettle. So this is how 3D works. Notice the presence of camera, the projection plane, and the world of coordinate axis, that is x-axis, y-axis and the z-axis, in which viewing transformation define how to acquire the image on the projection plane. So how we convert this 3D image into the 2D surface is all about the transformations and the projections. So for defining the three-dimensional scene, we using some metaphors for creating these 3D scenes, and these metaphors are coordinate camera using the U, V and N system, means it is the U rays, N rays and the V rays, and the 3 axes, that is x axis, y axis and the z axis, to view the 3D scene. So what are the steps in the 3D viewing is, first of all, projection type specification. We have to specify what type of object is and what type of surface you are using in which you are showing the object. So why this projection? Because we want to see in 3-dimensional, but we have the 2D surface. So we have to convert this 3D to 2D. So this is all about projection. And the two most important projections are perspective projections and the parallel orthographic projections. In this we have to use the parameters, that in viewing plane, I coordinate system and the scene coordinate system. So these three are the important factors we have to take care, that is what is our plane in which we want to see the image, what are our I coordinate And what are the c coordinate? I coordinate means it's u, v and n, and the scene coordinate are x, y and x axis, y axis and the z axis. Then we will cover the clipping part, that is 3D clipping, means clip against the view volume. What are the parts we can see, or we have to clip that parts only. And then comes the projection and display, window to viewport transformation. This is how conceptual model of 3D viewing process. In the 3D world coordinate, the output primitives, first of all we have to clip against the view volume, means what the volume we can see from our I coordinates, that part we have to clipped, means cut down. Then clipped world coordinates, then we have the processed image that we can see somewhere. That processed image is project onto the projection plane, and then that on the projection plane we have to transform into the viewport in 2D device coordinate for display, that is 2D device coordinates. So, the projection is transformation from ND coordinate system to MD coordinate, means from N coordinate system to M coordinate system, where M is less than N. So, our concern is N is M because object what we want to view is in 3-dimensional and the surface is 2-dimensional. So, our concern is N is 3 and M is 2, and the transformation from ND coordinate system to MD coordinate system is the projection. So, terminology what we are using here is projectors. Projector means straight projection rays, and then the center of projection where the projectors emanated from, and the projection plane where the projection forms. Then comes the projection from 3D to 2D, defined by how 3D to 2D is defined. So, projector emanate from center of point axis, passes through each point of the object and intersect the projection plane. And the planar geometric projections is projection is into a plane and it is referred as a projections here. Then there are two basic classes in which projections are categorized. The one is perspective projection and the other is parallel projection. So, perspective projection is distance between projection plane and center of perspective is finite, where area is defined very well, and the visual effects similar to the human visual system is present. So, the distance from center of projection is longer, size is smaller. As the distance increases, it is assuming that the size becomes smaller and smaller. Exact shape, measurement, parallelism is not reserved. This is the how we convert the 3D viewing system. First of all, we have to clip against the volume, means what we can see, we have to clip that part, and then the clipped world coordinate, the project into the projection plane, and then that projection plane is transformed into the viewport in 2D device coordinate for display, and then this 2D device coordinate will be seen to us. Then comes the key term projections, which from 3D to 2D is defined by straight projection rays, projectors emanating from the center of projection, passing through each point of the object and intersecting the projection plane to form the projection. We have two types of projection, the one is perspective and the parallel. The key factor is the center of projection, means what are the center of projection. If the distance to the center of projection is finite, then it is said to be perspective projection. If the distance to the center of projection is infinite, then we said the projection is parallel. Here you see, this is the center of projection. When we see this object, this distance is finite, that we can see only to this extent. This forms the projection and these angles form the projectors. Here in the parallel, projection is infinite. Here you cannot define the view. The view can be made infinite. You can see beyond the level. Then we said it is the parallel projection. So here are some differences between the perspective and the parallel projections. In the perspective projection, visual effect is similar to human's visual system, and it has perspective foreshortening, and the size of object varies inversely with distance from the center of projection. Here the angles only remain intact for faces parallel to the projection plane. And in the parallel projection, less realistic view because of no foreshortening. And however, parallel lines remain parallel. They do not meet each other at any angle at any point. And the angle only remain intact for faces parallel to the projection plane. And any parallel lines not parallel to the projection plane converge at a vanishing point. So, not the projection lines, but any other line which will converge at a vanishing point. So, there are an infinite number of these, one for each of the infinite amount of direction line can be oriented. If a set of lines are parallel to one of the three principal axes, the vanishing point is called an axis vanishing point. There are at most three such points corresponding to the number of axes cut by the projection plane. For example, if Z projection plane cuts the Z axis normal to it, so only Z has a principal vanishing point, and as X and Y are parallel and have none. So, these can be categorized perspective projection by the number of principal vanishing points and the number of axes the projection plane cuts. So, this is the one of the anomaly of the perspective projection, that is the vanishing point. But in the perspective projection, two different example of a one point perspective projection of a cube. So, here is the one point that the perspective projection can be formed. You have to note that X and Y parallel lines do not converge, so that these can meet the parallel projection. So, 2-point perspective projection include, this is often used in architectural engineering and industrial design drawings. 3 points is used less frequently as it adds little extra realism to that offered by the 2-point perspective projection. Here you see the 2-point perspective projection, where the view can be made from two sides, so that the different angle and the different view can be seen. This is known as 2-point perspective projection. And in the parallel projection, distance between the projection plane and the center of perspective is infinite, and it is less realistic view, and it does not have any foreshortening. So, exact measurement and the parallelism is preserved here. So, the perspective projection is, these are non-linear transformations. Perspective projections can be implemented with the matrix in the projective space followed by a divide by the homogeneous coordinates. This is very useful in architectural rendering, realistic views, etc. So, basically the uses of these projections is in the architectural design, where they create the view, front view, side view, two-way, one-way, etc. So, the one of the anomaly of this perspective projection is vanishing point, which is the point that set of parallel lines not parallel to the projection plane converge to the projection of a point at infinity. So, the axis vanishing point is vanishing point of a set of lines parallel to the one of the three principal axes, at most, that is x axis. If it is parallel to x axis, then it is said to be x axis vanishing point. If it is parallel to y axis, then it is said to be y axis vanishing point, and if it is parallel to z axis, then it is said to be the z axis vanishing point. And the example is, if the projection plane cuts only z axis, then only z axis vanishing point is there, as lines parallel to x or y axis also parallel to the projection plane. So, the number of axis vanishing points can be used to categorize perspective projections, which is also equal to number of axes cut by projection plane. So, number of axis vanishing point will be three types: the 1 point, 2 point and 3 point. The most usually used vanishing point is 1 point. Here you see, here it is x axis, it is y axis, and this is z axis. When you have to project this cube from this projection, center of projection is here, when you see, you can see only this one dimensional. This is known as the 1 point vanishing point. So, here you see the one side of this cube only. Then comes the 2 point. Here in this cube, you are seeing from 2 points, that is x axis and z axis, and your view is of two types, the one from this side and one from this side. This is commonly used in the architectural, engineering, industrial design and advertised drawing, this 2 point vanishing, the 2 axis vanishing point. So, parallel projection is, these are the linear transformations, linear means in one sequence, that are useful in blueprints, systematic diagrams, etc. Here you see these flat lines, these are parallel, these are not meeting at any point, they are running parallel, they are not meeting, they are not converging at any single point. So, this is known as the parallel conversion. The parallel projection is defined by two types, it has two types. The one is direction of projection, we will say DOP, and the other is viewing plane normal, that is VPN. So, orthographic is direction of projection and viewing plane normal, the same or the reverse. The next is oblique, and here the DOP and the VPN is not same nor the reverse. In the orthographic parallel projection, projection plane is perpendicular to the principal axis, and the most commonly type of orthographic parallel projection are front elevation, top elevation and the side elevation. Front elevation is what we are seeing from the front, top elevation is the projection of an object from the top, and the side elevation is projection of an object from one side. And it is used in engineering drawings such as machine parts. So, the parts of the machine can be described or can be viewed very clearly with these parallel projections, and it is very hard to reduce to 3D nature. So, we are using this parallel projections. Here you see the parallel projections. This is the top elevation. When you see the projection plane, the top view of this, here you see these slanting lines become this one, make the rectangular box from this top view. This is the one side, this is the other side, and the one side from this. This is the top view. This is the side view, what you are seeing, and this is the front view, what we can see from the front. So, these are the orthographic parallel projection. In the orthographic parallel projection, axonometric orthographic projection is there. So, projection plane not normal to the principal axis. Several faces of a object can be shown at once, and the parallelism is reserved here. Distance can be measured anywhere. So, the example of this isometric projection is VPN and DOP is equal to dx, dy, dz, where dx is equal to dy and dy is equal to dz, and it has the 8 directions. Then comes the oblique parallel projection. In the oblique parallel projection, projection plane normal and the DOP is different, and projection plane is normal to the principal axis, and the measurement of distance and the angle of faces parallel to the plane is allowed, and it is widely used projection. And the two types of this oblique parallel projection can be defined into two types. The one is cavalier and the other is cabinet. In the cavalier parallel projection, the DOP makes 45 degree with direction plane, and in the cabinet, DOP make angle of arctan 2 with the projection plane. Here you see the cavalier parallel projection, where we label this side 1 and this side 1. But in the cabinet type, this is the 1 and this is the half, means what is the view? We can only see the half of the box, but in this we can see the whole, so that we can divide or categorize these two. So, the classification of planar geometric projection are, the first, the planar geometric projection are of two types, parallel and perspective. Parallel projection are further of two types, orthographic and oblique. Orthographic can be top plane, front plane and side plane, and axonometric. Axonometric can be isometric and other, where the oblique can be cabinet and cavalier and other, and the perspective can only be divided into three parts, that is the 1 point, 2 point and the 3 point. Now, the specification of arbitrary 3D view is, view plane can be formed by the projection plane, which is defined by the VRP, that is the view reference point. Means, look at the point in the OpenGL, we will define the numberings so that we will refer the view with some identity, that is known as the view reference point. And the view plane normal, which is in OpenGL iLook part, which what we can see, that is the VPN, view plane normal. And in the window, it is similar to the window in 2D. Means window in 3D and the window in 2D is similar, but the content to be mapped to the viewport, that is projection on a view plane outside the window, is not shown. So, the specification needs the following: minimum and the maximum window coordinates, and two orthogonal axes should be mentioned here, which can be defined by the view volume. Next comes the specification of the arbitrary 3D view. In the projection reference point, in the parallel, DOP is equal to from PRP to CW, and in the perspective, the center of perspective is I in the OpenGL, that is generation language, and in the view volume, first of all you have to clipping and then project. In the perspective type, semi-infinite pyramid with apex at PRP and edges passes through window corner. And in the parallel, infinite parallel pipe with side parallel to DOP. Specification of arbitrary 3D view. In the view volume in the continuation of view volume, finite view volume front clipped plane is parallel to VRP and specified by front distance is equal to distance FCP minus VRP. And the back clipping plane is parallel to VRP specified by back distance is equal to distance BCP minus VRP. In the OpenGL, near and far represent front and back respectively in the camera coordinates. In the finite view volume, first there is front clipping plane, then view plane, then back clipping plane. And in the perspective, in the parallel volumes, these are the parallel lines which do not meet at each other at any point. But in the perspective, with the center of curvature, these are meet at one point which is known as the viewpoint. Next, the specification of arbitrary 3D view. It is mapping from view volume to 2D space, and the view volume is NPC, that is normalized projection coordinate, that is standard cube, and the 3D viewport specified in the NPC, that is normalized projection coordinate. If Z is equal to 1, face of NPC cube map to display, but if wireframe, then Z coordinate discarded, if surface, then hidden surface removal. Next is the graphical pipeline revisited. In the perspective projections, the I coordinates, first of all there are I coordinates, that is model view metric. Then this I coordinate make the clip coordinates, but the what eyes can see or what is the view at some point. Then we set the projection matrix. Then the clip coordinates means we only clip that part what we can see. Then there is a clip, then comes the normalized device coordinate, and the perspective division occurs here. Then at a viewport matrix, then the picture goes to screen coordinates. So how these pipeline work? First of all, these I coordinates, see that then the things are stored in the model view matrix, then the clip coordinate in the projection matrix, then clip, normalized devices, then come to the viewport matrix, and the scene is defined or seen at the screen coordinates. Here comes the perspective viewing with OpenGL. In the perspective transformations, here you see there is an eye which is can see in this part, and this is an object. This I to 1, I to 2, and here is the XY coordinate 2, 1. This camera for perspective projection includes GL metric mode, which includes the GL load identity and GL perspectives, and the parameters include view angle, aspect ratio, N and F. So this is the one of the values given to view angle, that is 60, aspect ratio 1.5, N is equal to 0.3 and F is equal to 0.5, and this makes this scenario and this graph will be occurred. So what we have discussed is the 3D projections, where The perspective is rays converging at eye position, means where an eye is seeing to the objects, the points are converging at some point. And in the parallel, rays are parallel to the view plane. So parallel projection can be defined into two